Dr. Craig Benson, collection of 7 papers, of which 4 I'll outline, on the use of geosynthetic clay liners, GCLs, has made him one of the world leaders in understanding issues related to their use. He has made extensive use of case histories and forensic engineering of full-scale applications to the understanding and behavior of GCLs in the field, how the behavior of GCLs is affected by the physical and chemical properties of the adjacent soils, how construction methods employed for GSL installation influence field performance, and how the environmental conditions to which GCLs are exposed influence field behavior. His practical design recommendations for GCLs has been adopted by GCL manufacturers and by practicing engineers throughout the world. As a result of these efforts, the practice selecting and using GSLs has been transformed. His paper, Effect of Wet-Dry Cycling on Swelling and Hydraulic Conductivity of Geosynthetic Clay Liners, Lynn and Benson, 2000, was the first to provide convincing evidence that the problems arose in situations where there was both dehydration of a GCL combined with cation exchange, and it demonstrated, based on laboratory studies, that these 2 mechanisms resulted in cracking of the bentonite in the GCL combined with the loss of normal ability of the bentonite to self-heal on rehydration. The consequence was a permanent and often significant increase in hydraulic conductivity. However, the full significance of this work could not be really appreciated until it was supported by well-documented field evidence. The field cases reported by Meir and Benson, 2007, Benson et al., 2007, and Scalia and Benson, 2010, provided the comprehensive evidence needed to support the concepts proposed by Lynn and Benson back in 2000 that was based on laboratory work. So you do laboratory theory and follow it with field trials. It is these case histories that have convinced the profession of the importance of considering the effects of desiccation and cation exchange when designing the GSLs, especially in cover applications. The case studies and the insights they provide for engineering practice have had a unique and profound impact on our understanding of the issues and steps needed to avoid problems in their use of GSLs in situations where they could potentially desiccate. They represent an outstanding contribution to the profession. Another paper of Dr. Benson deals with the critical importance of construction quality control when dealing with GSLs, especially in pond applications. Again, the evidence from extremely well-researched forensic investigations of a failure has provided critical insight and guidance to the engineering practice. This is another outstanding case history. Still another publication on hydraulic conductivity of geosynthetic clay liners exhumed from landfill final covers with composite barriers. This was in the Journal of Geotechnical and Geoenvironmental, and in 2010, illustrates how the hydraulic conductivity of GSLs placed beneath geomembranes is very sensitive to the moisture content of the subgrade. This study confirmed the dehydration hypothesis, but also illustrated how GSLs beneath geomembranes may never hydrate significantly and are still prone to alterations in hydraulic conductivity due to cation exchange. The findings indicate that this condition can be remediated by placing the subgrade soil at an optimum water content or wetter, a condition that has been adopted in practice. A 4th paper on preferred flow of geosynthetic clay liner exhumed from final covers with composite barriers. This was in the Canadian Geotechnical Journal in 2010, illustrates how some GSLs beneath geomembranes can develop preferential flow paths that result in excessively high hydraulic conductivity. The paper illustrates for the first time how GSLs hydrate by moisture that wicks up needle punching fibers, then migrates laterally. The aforementioned recommendation, placement of subgrade at optimum moisture content or wetter, is recommendation to prevent the problem and has been adopted in practice. As these descriptions indicate, Professor Benson has embraced the principles that Professor Peck and has transformed geotechnical practice for GSLs by conducting thorough case studies, performing forensic analysis, and developing a thoughtful understanding of the importance of geotechnical conditions where GSLs are employed. This collection of papers and the practical engineering recommendations they contain result in a fundamental change in the geotechnical engineering with GCLs, including new criteria for suitable applications, placement conditions, construction practices, and geotechnical testing methods. The comprehensiveness of Professor Benson's contributions aligns closely with the thought and comprehensive approach employed by Professor Peck. This award is an ideal way to honor Professor Peck's memory and recognize Peck's lineage of engineers in our profession. Professor Benson is a direct academic descendant of Professor Peck. His major advisor, Professor David Daniel, was an MS and PhD student by Professor Roy Olson, who was a PhD student of Professor Peck. It is a pleasure to participate in the prestigious Ralph Peck Award and Lecture. The award was established in 1999 by the Geo Institute in honor of Ralph Peck. The Ralph P. Peck Award is presented for outstanding contributions to the geotechnical engineering profession through the publication of thoughtful, carefully researched case histories, or the publication of recommended practices or design methodologies based on the evaluation of case histories. The 2012 Peck Lecturer is Dr. Craig H. Benson from the University of Wisconsin-Madison. Craig, would you please come forward to accept the Peck Award? For your collection of case histories in forensic engineering to understand the engineering principles necessary for the appropriate environmental applications and hydraulic design of geosynthetic clay liners as hydraulic barriers, I present you the Ralph P. Peck Award. Congratulations again.
Thank you, Phil. Wow, quite an introduction. I really appreciate that, Phil. It's nice to be here today. And is this a little bit too loud? Sounds a bit too loud to me. Okay. It's great to have an opportunity to talk to you about something that I've spent 15 years working on, maybe even a little longer. Also something that I believe illustrates principles that we use every day in our research environment, and I'll talk a little bit about that. But I had a much longer-winded title early on and a longer presentation, and as I thought about this, I needed to narrow it down. As I've gotten older, I found that I talked longer, so I'm going to narrow it a bit so we're done in 60 minutes. But we're going to talk about geosynthetic clay liners, our bentonite barriers, and what we've learned from the field and how our observations in the field have informed what we do in the laboratory, and then what we learned in the laboratory informs our theory, and then our theory informs our practice. So there's a loop, an important loop. I wanted to also show just a little bit of lineage. I always find these family trees really interesting. I don't think we think enough about this, but what I found over time is the way people approach problems is really driven a lot by the people they've worked for, their mentors, and who their mentors work for as well. And so there's my family tree. Two particular mentors who I worked with extensively, Dave Daniel and Roy Olson. Roy's looking pretty tough there. He's a tough guy. Dave's smiling, but he was equally as tough. But both very good mentors and people I learned a lot from. And of course, that flows from Professor Olson's interactions with Professor Peck when he was at the University of Illinois. And this philosophy of joining practice and research together is really something that I think all these individuals embrace, and certainly is something that's very intrinsic to my practice as well. Some remarks from Professor Peck that I have adopted a little bit. I shorten them a bit. I think one of the first ones is, the first bullet here is really a cornerstone of the things that we do in my group. Really, we focus on practical problems. We start with some problem and that needs to be solved. And then we begin with that problem, and then we dig into it, we understand the mechanisms, and then at some point we're able to essentially change the way that problem is tackled or approached later on. But it all begins with a problem, and I think that's a characteristic of the colleagues that I work with at Wisconsin. We are very practical problem-oriented in our research. Another bullet from Professor Peck was that we need to have field information to confirm what we believe in our theories and in our laboratory. We have to be sure that things are borne out at full scale. This ability to transform from bench scale to field scale, from theory to practice, is an important part of what we do. And that's really, I think, very much a key component of our discipline. And finally, the last bullet, and I didn't ever know Ralph Peck embraced this until I was studying it in the last week or so, but this is something I truly believe in. Whenever we try to force our assumptions on nature, as engineers, we often run into problems. We should always be considering nature as a model, and looking at natural systems and understanding how they behave is often a way to engineer systems that will perform well over the long term. So a healthy respect for nature is a valuable standard to work by. So as I think about my work and what I'm going to talk about today, and I think this really embraces a lot of what Professor Peck did throughout his career, and my mentors as well. We had research that was informed by practice. That's where we started. We had research that was dealing with a practical problem, usually field observations. That then evolved into a collection of work, and then our practice then was informed by our research. And these two go back and forth. And I think of it at the very bottom of this slide. Really, we start with observation. We conceptualize a mechanism. We develop and understand the mechanisms and quantify them, and then we build that back into our theory, and then we create informed design. And this loop continues. It's an important part of the way we approach our practice. So how does this all fit into geosynthetic clay liners? I think that'll be clear as we go through this. These are really, really neat materials. I think these are really revolutionized the waste containment industry. First used around 1990, and essentially have used in lieu of clay, traditional compacted clay barriers, and in effect over the last 20 years or so have replaced clay barriers as essentially the mineral barrier of standard barrier that we use in practice. GCLs have been very widely adopted. In essence, we have a roll, almost looks like a carpet right here. A carpet-like structure that we roll out, place it a lot like a carpet, and you can see sheets of it that have been deployed here and over here. Roll it out, overlap it. Sometimes we'll put some bentonite within the seam, and we're done. It's a very quick, rapid, and effective construction process that saves money and can function very well. Certainly much more expedient than constructing a compacted clay liner. What do these materials look like? They're really interesting materials. We'll have two geotextiles, typically a geotextile on the top and one on the bottom, some needle punching holding them together, and internally filled with granular bentonite, so nearly dry bentonite. And this almost looks like a sand-sized material, and when you look at this figure, it looks extremely permeable. It looks like water would flow right through it, right? But what's really interesting about bentonite materials is that when we hydrate them and the sodium interacts with the water, we start with a granular material that transforms into a gel-type structure that we show at the bottom here. This transformation is really critical to the success of these materials and what makes them truly unique barrier materials. The ability to transform from something that looks sand-like to something that looks very amorphous is the key attribute of these materials that makes them successful. That's both a physical phenomenon, but very much a chemical phenomenon as well. And understanding both the physical component to this and the chemical component is essential to understanding the behavior of these materials and for proper design. And I think this has been one of the things that we've toiled with over the last 10 years to really understand the coupling of these physical and chemical processes. And that's largely what we're going to talk about today. Well, where did this get started? I said our research is really driven by problems, practical problems. I got started working on these physical and chemical interactions of bentonite probably about 15 years ago with my colleague, Professor Tuncer Edel. We were dealing with interesting large-scale case histories, one of them being a big mining project in northern Wisconsin for a tailings facility where we were trying to contain a leachate in that tailings facility that had a collection of different metals. And then another case history that had come along. So one was a liner problem, this tailings facility, and the other part of this was a cover problem, a barrier system being placed over a coal ash facility in southwestern Wisconsin. And that's what I'm going to start with today, is this latter case history, this cover. But these were both problems that came up around the same period of time, dealing with GCLs, and it was the practice that informed the research. It began with a practical problem. To illustrate here, this is a surface barrier or a cover that was being placed over a coal ash facility. If we look at the surface materials, we have some vegetated surface layer, and I have some of my engineering plants in it. You can see right here. My plant physiologist friends always make fun of my plants. They look far too simple. But I do have some roots in them, and those roots penetrate down through our surface layer, and at the bottom of that is a GCL. That's our hydraulic barrier. That's what's supposed to be our impedance to flow, preventing precipitation that would be up here in the atmosphere from making its way through the system and ultimately getting into the waste below. So the idea here is a hydraulic barrier, a clay barrier, this GCL being placed beneath some superficial vegetated cover soil, and this final cover altogether was meant to minimize the amount of liquid that would enter the underlying waste. Now, this was the first GCL that was deployed in Wisconsin at the time in a final cover. And our regulatory agency is kind of known for being skeptical, one might say. And I think rightly so. They said, well, this is a neat idea. We'd like to try this out. But why don't you prove to me that it's going to work? And I think as engineers, we have an obligation when we say things are going to work, we ought to be able to measure it and prove it, right? And the engineers who designed this were very confident in this. They were willing to put in large pan lysimeters, essentially a big bathtub underneath the cover that would collect the liquid that came out and monitor the flow. And that's what we see underneath the cover here. This is a lysimeter. This is their design. This is not ours. It's essentially a pea gravel filled pan, has a still well, a pipe that goes over to a still well, and they would collect the water and measure the percolation rate on a periodic basis. A very simple system. And the engineers were very confident that this would work. Now, if we know that GCL is a hydraulic conductivity of roughly about 2 × 10⁻⁹ centimeters per second under stresses typical of covers. And if you do some simple calculations, understanding the variation in gradients throughout the year that we see in cover systems, I would expect somewhere on the order of a few millimeters of flow through the system a year. So we would expect on the order of 1, 3, maybe even 5 millimeters per year, depending on the assumptions. So they began monitoring this, and the results were surprising. This is cumulative percolation on the left and time on the right. This is data that were collected by the engineers who designed this facility, and I graphed it up later, but it's their data. And early on, and remember I said a few millimeters per year, and now notice my scale, I've got 1,000 here, all right? So everything, I guess, is within a couple orders of magnitude. But we see, and this is in years, within 1 year, one of the lysimeters, there were 2 lysimeters, is indicating that the percolation rate, what's flowing in through the cover system, is much higher than was anticipated. In fact, it's appreciably higher, probably 2 orders of magnitude higher, at least in one of the lysimeters that occurred early on. There was some concern at the time that that lysimeter had a flaw in it, that there was something done inappropriately, so they went back and reconstructed it from scratch, ripped it out, rebuilt it, and began collecting data again. So there's a reconstruction here, and you don't see the blue points, but it began again. And again, about a year later, the percolation rate was climbing very high, much higher than anybody expected. And a little later on, the lysimeter, too, for some reason it was delayed some, but it showed a similar type of behavior. The percolation rates tended to climb. So there clearly was something that was not functioning the way we anticipated. So we begin here with an interesting problem. Something that we thought was going to function one way is behaving very differently, and the question is why? Well, we went and had the opportunity to, I do a lot of digging things up. People who know me and who work with me know that I spend a lot of time in the field down in pits looking at things, and this comes back to this idea of observing phenomena and using that observation then to drive our understanding of developing conceptual models and mechanisms, and ultimately informing our practice through understanding the processes. But it begins with observations. And this is one of the interesting observations we made during the exhumation. This is the bentonite that's meant to be the hydraulic barrier in this particular case. Doesn't look very impervious. Doesn't look like that gel that I showed you earlier. In fact, it's got lots of cracks in it, right? It looks very permeable. This is a photograph that Brian Albright, one of my former PhD students took circa about 2000. We exhumed the GCLs in these lysimeters, and we found some very interesting behavior. We did this at 2 different times, too, in 1999 and then in 2002. One of the things that we found is that the water contents were quite a bit lower than what we expected, particularly in 2002. In our second exhumation, they were down on the order of 20 or 30%. We hydrated GCL in the laboratory. We would expect water content on the order of 100% or so. These are much, much lower. The other thing that we observed, when we measure the swell index, this is a measure of the swelling potential of the bentonite. The new GCL was about 24 milliliters per 2 grams, the kind of odd units that we use for swell. Our swell index for these bentonites that we were taking out of the GCLs were appreciably different. So the swelling potential of this material had changed. It had been transformed during its life, relatively short life, of a few years within the cover system. And the hydraulic conductivity of the GCLs was very much higher. And again, here a new GCL down in that low 10 to the minus 9 range. One of them being a little bit higher, the others being appreciably higher. So the hydraulic conductivity had increased orders and orders of magnitude, which is consistent with those cracks that we saw earlier. So the question is, why was this occurring? We know bentonite is a highly swelling material. When it can dry and shrink and crack, and we expect when it rehydrates, it will wet back up, it will swell, and those cracks will seal shut. At least that's our underlying hypothesis. So we're beginning to question whether that hypothesis is valid. At the time that we were doing this, Steph Melchior, who's a soil physicist in Hamburg, had been doing almost identical work at the Gerswerger landfill in Hamburg. He hadn't built lysimeters, but he had buried GCLs and had let them sit in the ground for a while, and then was exhuming them and finding similar types of behavior. He hadn't measured the hydraulic conductivity at the time, but he exhumed them and found they were filled with cracks. And then later on, a couple years later, he had exhumed them again and measured the hydraulic conductivity, and we're seeing the same kind of things that we did. And we began to wonder, what were the mechanisms driving this? We know in cover systems they have a very periodic wetting and drying process as part of the hydrology of the system. So that was clearly a clue or something we were thinking about, that there was some wet-dry cycling that was present that was driving this process. So we began with some very simple experiments. This is Ling-Chin Liu, who was one of my master's students in the late 1990s, where it was very simple experiments. We always believe in starting off with something very simple and then building up our knowledge base and then beginning building things that are more sophisticated as we go forward. But these were simple experiments where we would take a sample of a GCL, one of these, essentially a disc. We would permeate it in our laboratory until we got to a steady state condition, and then we would pull it out of the permeameter and set it on the lab bench and let it dry. And we would record the mass over time and wait till it stopped drying, so essentially it lost as much moisture as it would, at least within the thermodynamic conditions of the laboratory, and then we would begin that process again and permeate it. And this is the type of behavior that we saw. Early on, we were running these experiments, and these experiments roughly take at least 2 months per data point here. So these are not a simple little test, all right? And we're going on roughly about a year, and Ling's getting worried that she's got a kind of a boring thesis because we're down in this range. And nothing's happening. And she's thinking, am I ever going to graduate? And then things started to change. There was a transformation. And 2 of the experiments that we ran, where we used a calcium chloride as the pour water in the permeate solution, we started to get changes in the hydraulic conductivity. The hydraulic conductivity began to increase. Whereas with the specimens that we permeated with just deionized water essentially remained unchanged. So there was a chemical interaction here. And the calcium is important because we know that bentonites that we use in GCLs and other environmental applications are sodium bentonites. There's a sodium cation that's the predominant cation that's associated with the mineral surface. And we'll see in a minute why that's particularly important in terms of the swelling behavior of bentonites. But we know in the environment that the most common cations are the divalent cations, particularly calcium and magnesium. They're the most predominant cations in the natural earthen materials. The other thing that's, if we go back and look at the soil chemistry literature, we see that there's been a lot of study. There's been a lot of study on just about everything. It's one of the things I'm always amazed by. If you're working on something, somebody has probably already touched it already. But Garrison Esposito at Berkeley had been doing work on looking at the chemical thermodynamics of calcium for sodium exchange on bentonites. And he was able to show very elegantly that it was thermodynamically favorable for calcium to replace sodium, magnesium to replace sodium. So wherever we put a sodium bentonite in an environment where there's calcium and magnesium, the calcium would migrate towards the bentonite and replace the sodium. It was very thermodynamically present. So that was part of what was going on here. There was this exchange that we observed, and that exchange was driving changes in the behavior. And we'll see more of that as we go on. One interesting thing here, we did run these experiments with DI water out to about 5 cycles and had no change. And you could argue that we might have needed to run those experiments a little longer and see if we saw any change. But we have a couple other things in our laboratory that drive our practice. These experiments here in green took about 2 years, and we have what's called a graduation termination criterion, where students at this point say, I'm not going to run any more tests, I'm leaving, all right? And that's what happened with the green ones. Ling Chu said, I'm done running experiments for you, Professor Benson. I'm going to graduate. So what did we see? The other thing that we looked at this was swell index of the bentonite. And if you remember, again, the test we ran with the calcium chloride as the permeant water, the hydraulic conductivity increased appreciably. Those with deionized water, essentially a water which would not alter the chemical state of the bentonite. The bentonite would stay in its sodium or sodic state. Those remained essentially the same. And if we look at what we see from the free swell of the bentonites in those GCLs, those permeated with calcium chloride actually began to diminish. All right, so there was a process that was occurring, a chemical process that was altering the physical behavior of the bentonite. It was losing its ability to swell, and the swelling capacity and the formation of that gel structure I showed early on is really key to the success of bentonites functioning. In contrast, if we permeated them with deionized water or tap water, they remained essentially the same. So no alteration and a very significant alteration. And you'll notice that on my previous slide, I showed that transition in hydraulic conductivity with the calcium permeants was right around 4 or 5 cycles of wetting and drying. And we see on this graph here that right around 4 or 5 cycles, we've really kind of bottomed out on the swelling capacity. So the bentonite is transformed from a highly swelling material to a material that swells very modestly and doesn't have the capacity to potentially heal cracks, as we'll see in a minute. So there's actually been a great deal of work understanding the thermodynamics and the chemistry of calcium and magnesium and sodium in bentonite materials. There's actually a whole plethora of articles on this that go back to the 1950s. This is a classic paper that was published by Norsch in 1957, a graph from his paper, where he articulated the different components of bentonite swell. Bentonite, if you remember, is predominantly comprised of montmorillonite mineral, and montmorillonite mineral is a 2-to-1 mineral. So we have 2-to-1 sheets. Those 2-to-1 sheets are fairly weakly bonded together, and when the bentonite is placed in water, the montmorillonite will hydrate. That means that the water molecules are associating with the charged mineral surface, and those sheets will separate. All right? As opposed to in other minerals where they're fixed, where there's a strong bond. In montmorillonites, they separate. Water molecules make their way in between the montmorillonite sheets, and that's what drives this. That's what makes bentonite such a highly swelling material. The sheets separate, water molecules fill that inner layer region, and it expands appreciably. What Norris showed were 2 things, is that swelling process occurs in a couple of different steps. The first step is what he calls crystalline swell, where it's essentially where the first steps of hydration occur, where the first layers of water molecules associate with the montmorillonite surface. That results in a swelling of roughly 2 nanometers. We call that crystalline swell. That's in this region here. And then another transition occurs that we go into a phase called osmotic swell. Osmotic swell, where we end up with appreciably more swelling, or essentially expansion of the inner layer in the montmorillonite mineral. We talk about that inner layer in terms of something called the D001 spacing. Those of you, I imagine everybody in here has looked at Jim Mitchell's book, Fundamentals of Soil Behavior. If you go back on the clay mineralogy section, you'll see the D001 spacing. Essentially, this is just a measure of essentially the separation of those platelets. So we could use this D001 spacing shown here on the y-axis and just replace that with the word swell. We could just put swell right there. And the other thing on the x-axis is the reciprocal of the concentration. All right, it's kind of an unusual graph, and I think Norrish plotted it this way just to make it linear. But this is 1 over the concentration on the x-axis. So if we go to the right, we're in more dilute solutions, and on the left, we're in concentrated solutions. So there's a couple of things that he observed here. As solutions were more dilute, we got more swelling in bentonite. Very dilute solutions, we got a lot of swelling. And if it was very concentrated solutions, on the other hand, we ended up with very little swelling and perhaps only crystalline swell. The more dilute, though, the more swelling we got. This osmotic swell is really an important part of this. This is this component of swell in bentonites that gives it that gel structure, that gives it that kind of greasy feel, that plastic feel in your fingers. That's the osmotic swell component. Without that, bentonite does not behave the way we would like it to do and in the way that we rely on in many applications. The other thing that Norrish showed was not only this concentration dependence, so clearly a very concentration dependent behavior, but also a cation dependent behavior. He showed that when the cations associated with the mineral surface were monovalent, sodium, potassium type of cations, we got both crystalline and osmotic swelling, that we would get the potential for very large amounts of swell. When they were divalent cations, like calcium and magnesium, osmotic swell was no longer present. We only got crystalline swell. And so if we have bentonites that are primarily calcium and magnesium bentonites, they don't swell. Those with primarily sodium cations on the surface do swell. So a fundamentally different behavior between a calcium magnesium bentonite and a sodium bentonite. And this goes way back to the 1950s from Norrish's work. And I think this photograph illustrates this really nicely. We took a bentonite essentially at the same mass per area as we would have in a GCL. And we ran the old GRI swell test. This is a test where you would take the bentonite out of the GCL, you would put it in a CBR mold, you would put a CBR plate on top of it, and then you would put an LVDT on top of that. And then you pour in water into the mold, and you would watch it swell, and you would just record the swell. And you would end up, if it was swelling a lot, you'd end up with this large patty here that you see on the top. I lost my mouse there for a second. There it is again. This is a bentonite that's been hydrated in deionized water. Look at that tremendous swell, that gel structure. It's really transformed from a granular material to a gel material. Let's replace the pore fluid from deionized water to a stronger calcium solution where that calcium will replace the sodium in the bentonite. Very different behavior. All right. What do we see here? We see virtually no swell. You can almost, if you look carefully, you can see the bentonite granules in this slide. So there's been virtually no swell at all. All right. So same material, but very different physical behavior depending on the chemical condition. So the chemical condition alters the physical behavior, and ultimately is going to alter the hydraulic conductivity as well. If we look at this as well, some photographs, it's actually Joe Scalia prepared these for me. These are, I think, illustrate this as well. This upper photograph is a sodium bentonite, again, hydrated in deionized water, all right? Forms a gel-type structure. You can see some of the original granules. The same material, but with a calcium bentonite. Again, it looks like sand. So one is very impermeable. The gel structure is very impermeable. And the granular structure in the calcium bentonite, as you can imagine, is very permeable. So the chemistry is really important in this linkage of chemistry and physical behavior. And if we look at a dry GCL specimen, after it's been dried, you can see it's got a whole bunch of different cracks in it. Here's one of our neat laboratory instruments, by the way, our plastic plate, lunch plate in our lab. Again, we tend to use very practical tools. But you can see the cracks in the GCL. If this GCL is going to be effective when it rehydrates, when it wets back up, that bentonite needs to swell, those cracks need to close. If the bentonite loses its ability to swell from a transformation from a sodium or sodic form to a calcium magnesium form, and it loses that ability to swell, those cracks won't close, and that's what drives the increases in hydraulic conductivity. So, our behavior at this point, as we understood it, this behavior that we saw in the field with very high hydraulic conductivities we attributed largely to calcium and magnesium exchange coupled with wetting and drying, and the inability of the transformed material to reheal itself due to its loss of swelling capacity due to the change in the chemical structure. Interesting, a little bit of data here as well. Later on in the project, they replaced the original GCLs with a geofilm laminated GCL, so a composite where the GCL actually has a geomembrane laminated to the surface on top, replaced that and reinstalled it, and the percolation rates to this day, actually, this graph actually should have some data way off on the right here now, remain very, very low at this site, on the order of a couple millimeters per year. So the laminated product, the geomembrane and GCL combination, worked exceptionally well. And we'll talk about that in a little bit. We were really interested in this. So we wondered how general this behavior was. We had this one case history, and of course, we can't draw generalities from one project. I certainly had a friend over in Germany who had observed this. We had observed it. It looked like this was an issue. I wasn't sure how common this phenomena was. So I, you know, like a lot of good academicians, you start pinging your federal agency folks and say, hey, I got an interesting idea. Can you help me fund a study to do that? And so I did that, and we started off with a small study where we went off and exhumed 4 different covers and around the United States, 3 of these, as you'll see, in Wisconsin and 1 elsewhere, to look at the condition of the GCLs. I just have one site. I wanted to see if this was more general. And I picked these sites in a way that I thought would help me with my hypothesis. I had 3 covers over here on the right, which were essentially a soil, vegetated soil layer over a GCL. And they ranged in thickness between about 600 and 800 millimeters thick, with a GCL at the bottom, different subgrades underneath the GCL. These were essentially like the earlier case history I showed, just different sites. Now, the assumption here is that the wetting and drying is one of the driving mechanisms in this process. The other assumption is that the calcium and magnesium are exchanging for the sodium, and that one of the things that where we believe that calcium and magnesium was coming from was water percolating down through the cover soil, eluting the calcium and magnesium from the cover soils, as we know occurs, and that calcium and magnesium rich water making its way down through the cover soil, contacting the GCL and altering its behavior. So our thinking was, if we found a site where there was a geomembrane over the GCL, this would essentially eliminate the source of the calcium and magnesium from above, from this percolating water, and it would also eliminate the wetting and drying that we observed as well, because we'd have a plastic sheet over the GCL, which should cut off the wetting and drying. So I picked this site S particularly as essentially my control to prove my hypothesis. And I'm always careful about that word prove, because whenever I say I'm proving something, I usually end up being humbled, as we'll see in a bit. But that was the intent here. We had a composite system over here on the left, with a geomembrane over the GCL as essentially our control. No wetting and drying, no calcium and magnesium from above. I should pull that GCL out. It should look like the day I put it in, just hydrated. It should be a nice, soft, supple bentonite, very impermeable. These other sites may be quite different. So we embarked on this very fun project to go dig these up. I said we spent a lot of time in pits digging things up and observing them. The 3 different sampling locations in Wisconsin. At the same time, my friend Clark Lundell of Republic Services was very interested in this, and he had a site in the Atlanta area where he had a lot of leachate in his landfill, and he couldn't figure out why, since they had capped it, and usually their sites, their leachate generation rates drop off appreciably after they cap it, but he was still getting a lot of leachate. So, and it had a GCL on the cover, and so he asked me to come down to this site O, and down in Georgia, and exhume the GCL there as well. So we had the 3 blue dots are the GCLs without a geomembrane, and the red dot at site S, that's in Sorona, Wisconsin, was the site with the geomembrane over the GCL. So we went out and dug them up. We do everything by hand. We dug this big, deep pit. No, we got a backhoe out there, dug down close, and then we did this stuff, all right? So we dug it out, though. This is actually at one of our site E. I'll talk about a little bit later. But we exhumed the cover soils, and then we exhume samples of the GCL. And the way we do this, I'll show you just a detail in the next slide, but these are some PVC panels. We put a lot of attention to minimizing disturbance of the bentonite when we extract the sample. So we have these PVC panels that you see here that are placed on top of the GCL. Get my mouse to move again here. There it is. It's a PVC sheet. These are about 300 millimeters by 300 millimeters and probably 5 millimeters thick. Just meant to be a nice stiff material. We cut around the perimeter of that, so we cut the GCL cleanly, and then actually we'll pull and slide the GCL on top of it, as you'll see in a minute. So you can see there in my right hand, I've got a razor knife, and I'm cutting the GCL, scoring it right around the edge. This is Jim Olsta, by the way, from Setco. I'm really grateful to Setco. They're a GCL manufacturer, and they've been very helpful in this work and helping us understand it and supporting it not only financially, but actually going out in the field and working with us. This is our site in Boardman, Oregon, by the way. So here's a picture of exhuming the GCL. So we've scored it around the edge, cut it with the razor knife, and then we very carefully slide the GCL onto this PVC plate. And then we'll wrap it with plastic to prevent it from desiccating, and we'll actually bury those plastic plates in a series of tubs. We try to keep stress on the GCL to provide any stress relief. We can't simulate the whole cover system, but we try to get at least roughly of 1/3 of a meter on top of the GCL if possible, if not even a little bit more. So we bury them in tubs and bring them back to the laboratory. So here's some of our data, all right, from these GCLs that we exhumed. So remember, I have my control, this one at Site S. I wonder what was going on. That was proving my point, all right? And I talked about being humbled, all right? Humbling is always a good experience. You learn from being humbled, although sometimes it hurts a little bit. Let's talk about the GCL-only sites. First of all, here's one that behaved a lot like the site we already talked about, very permeable. We had our site in Georgia where we had very high hydraulic conductivity, some very low, one in the middle, so quite a variation. And then one somewhere in between, the Site D. This is up in the Chemaquin National Forest in northern Wisconsin. The Site D where we had kind of intermediate hydraulic conductivity. So interesting. We didn't see precisely the same thing we saw at that one case history. We actually saw different types of behavior at different sites. And interestingly enough, the control perhaps had the most permeable samples. And that really got us thinking, what's going on there? To this day, this has not been proven out, but I will get to more on that, why that is in a minute. But this was an important learning experience for us as well. The other thing that we saw is we ran swell index on the bentonites from each of these GCLs. And for the ones that we exhumed here, lost my cursor, keeps going in and out. There, oh, well. If we look to the left on the free swell graph, you see that in green, the free swell, this bentonite that was used in these GCLs, when new, is roughly about 35 milliliters per 2 grams. All of the GCLs we exhumed had swell indices around 10 or lower. That's the swell index associated with a calcium bentonite, not a sodium bentonite. So it started out at 35 and transitioned to 10 over a service life of 4 to 8 years, roughly, depending on the site. If we looked at the relative abundance of sodium in the exchange complex, essentially the collection of ions that are cations that are balancing the negative charge on the surface of the bentonite, typically in the bentonites that were used in these GCLs, about 80% of the cations were sodium. When we looked at the exhumed GCLs, at most 20%. All right, so there's a great depletion of sodium in these materials. So again, the physical process and the chemical process are coupled together. We had a transformation from a sodium bentonite to a calcium magnesium bentonite, which altered the swelling behavior and altered the hydraulic conductivity, but still doesn't explain why we got this variation in hydraulic conductivity from site to site. Interestingly enough, I talked about that composite system, right? We put the geomembrane in there, and that geomembrane was meant to cut off the water from above that would carry calcium and magnesium and prevent exchange. And yet it was completely exchanged. At our site S here, the swell index is around 10, and most of the sodium has been replaced by calcium. What's going on? This isn't something we expected at all. Very different. Well, the water content was an important issue that differentiated the data that we observed. The GCLs that had become hydrated and remained hydrated, essentially became wet and remained wet, retained lower hydraulic conductivities. Those that had dried, potentially going through a desiccation cycle or several, had much higher hydraulic conductivity. So there was a clear dependence on water content, that if we got the GCL wet and it stayed wet, it tended to have low hydraulic conductivity, whereas if it hydrated and perhaps desiccated, it tended to have high hydraulic conductivity. So the variation in hydraulic conductivity that I showed on the other graph was very closely tied to water content of the bentonite. The wet bentonites had low hydraulic conductivity, the dry bentonites had much higher. That they had undergone shrinkage and cracking and became more permeable. And that threshold was somewhere around 80 to 100 in terms of the water content. Now, just to prove this was our hypothesis, that these specimens, the wetter ones, hadn't desiccated. We took these specimens, most of them, over here, and we dried them. We did some of these on the bench. We just set them on the bench and let them dry. Other ones, we simulated the state of stress appropriately and dried them under an overburden pressure, replicating the field. And that's what we see over here on this right slide. These are the low hydraulic conductivities associated with those wetter specimens. We dried them back to water contents characteristics of what we saw in the drier specimens in the field, and then we measured their hydraulic conductivity after a single cycle. And what we see here is that these low hydraulic conductivities down here, through drying, became much more permeable. And this was true regardless of whether we applied stress during drying or not. At the time, that was one of the issues, was the level of stress and whether that was important. Turns out it is important, but it wasn't a driving factor. And the issue here was this water content was important. We were able to illustrate that maintaining the water content and preventing desiccation was a key part of this process. And just to look at one of these GCLs, you see why that is. Here's an example. We have a crack in it. You can actually see some of the granules here that haven't fully hydrated as well, still in the bentonite of the GCL. So if it can't heal up those cracks, it will remain fairly permeable. So the other aspect of this, I'm just going to back up just briefly, is that if you look at these hydraulic conductivities on the wet ones, I'll let my cursor keeps going in and out, that they're low, but they're not as low as what you'd expect for a sodium bentonite right out of the box. Again, I started off saying it's about 3 times 10 to the minus 9 centimeters per second. For a GCL with deionized water at 10 kPa, that's about what you get. Almost every specimen you'll run at that stress level will give you around 2 or 3 times 10 to the minus 9. These are an order of magnitude more permeable, all right? Maybe 50 times more permeable. Why is that? We began to wonder about that as well. They are wet, and so it's not a desiccation process. There's something else going on. Well, we had the opportunity to run some very interesting experiments where we ran a long-term hydraulic conductivity test with a GCL with a dilute calcium solution. It's a 12 millimolar to simulate a natural pore water. This is another one of these graduation termination criterion tests. These are long tests, all right? See, 1,500 days, all right, at the end. You have to have patience to run these tests. But what you see is that early on, the hydraulic conductivity remains low, and then it's gradually increasing, all right? So there's some chemical interaction here as well that's altering the physical behavior. The hydraulic conductivity is changing as the permeate interacts with the surface. And in fact, what is happening is that it's transforming from a sodium bentonite to a calcium bentonite, and that too is altering the behavior in exclusion of wetting and drying. Just the calcium itself was altering the behavior as well. And so we ran these experiments, again, very long term. It increased up to about 10 to the minus 8, or roughly an order of magnitude or so, very similar to what we saw in those field samples, about a factor of 10 higher, and then it remained roughly about the same for almost 5 years. And then this student also wanted to graduate. He told me he wasn't going to run this test for me anymore. And I said, well, just do one more test. Just do one more test, and then you can leave. Maybe I learned this from Ken Stokey. Ken, you have a way of doing that with people, all right? And so I said, just take that specimen out of the permeameter and dry it to a typical field water content that we saw in the field. Just dry it to 50% for some of those more permeable specimens. He did that, and then he repermeated it, and we jumped up from 10 to the minus 8 up to almost 10 to the minus 5. Very similar to what we had saw from those exhumed samples. So those exhumed samples, again, we're in the field, we're having a transformation from a sodium bentonite to a calcium magnesium bentonite. If it remained wet, it had a low hydraulic conductivity, although not as low as we would initially expect with the sodium. If it went through that transformation and then dried, it changed dramatically. And we had a much more permeable structure. So we saw there's a physical and a chemical linkages together. So what's going on here? I talked about we start with conceptualization, observation, conceptualization, building in mechanisms, and that then drives our theory. So this is our starting off, just a little illustration of the mechanisms that are occurring in the bentonite during these different phases. We'll start off with our 2-to-1 sheets in our montmorillonite mineral here with some sodium on it. Those are the green circles in the inner layer. That space between the sheets is called the inner layer. And we add some water to that material, and we have that crystalline swell. We get a couple layers of water molecules in there starting to swell the bentonite. And then we go into an osmotic swelling process, depending on the concentration of the solution, and we get more swelling. That's that osmotic swelling. That gives us that gel-type structure. All right, that's what gives us about 10 to the minus 9 centimeters per second. Fully hydrated sodium bentonite right out of the box. All right, we'll change that a little bit. Let's now have some, we're in the field, we've hydrated, it's a sodium bentonite, but there's also a preponderance of calcium and magnesium all around this bentonite, and we know thermodynamically that calcium and magnesium are going to replace the sodium. And so what we see, slowly we'll have some of these calciums move in. Again, we have to have charge balance, so we'll replace 2 of the sodiums for every calcium. And we see some collapse of the inner layer water due to the presence of that calcium. And so it's contracting, all right? So that swell is actually being reduced some, but not dramatically by the presence of the calcium. So a lot of that water is locked in place essentially electrically with the mineral surfaces, but we do get some compression of that inner layer water when the calcium occurs. And that's what's actually driving that change from about 10 to the minus 9 to 10 to the minus 8, that transformation from sodium to calcium bentonite, and a modest reduction in swell and a corresponding increase in hydraulic conductivity. Now let's dry it out. We're in the field, it desiccates, we have root water uptake, it's drying the bentonite. We've taken that water out, but now we have a bentonite that's a dry bentonite, but it's a dry calcium bentonite. All right, it's different. It's not the same material we started with. And it wets up again, and it gets 2 layers of water molecules associated with crystalline swelling, but now it's a calcium bentonite. Now it's rehydrating in the field, and this is all it does. All right, this is where it stops. The osmotic phase no longer occurs. It's a calcium bentonite, and we know that calcium bentonites only undergo crystalline swelling, and that's the end of essentially the swelling process. And so very consistent with what we see mechanistically and what we know about the behavior of calcium and magnesium bentonites. Well, that doesn't answer our question about the case where we had the GCl plus the geomembrane, our proof case that ended up being the humbling case, this one with a question mark. I was interested in this, and so I went out and convinced some folks that we ought to dig up more of these and find out what's going on with the GCLs overlain by geomembranes. So we did that. We looked for sites that had cover systems that had a composite barrier. So we had, again, a GCL overlain by a geomembrane, typically in a structure that looks like this, and then we exhumed it. We did 2 sites out in the west. Apple Valley, California, a community that's never had an apple tree. That's a developer's idea. My brother lives right next there, so I go there very frequently. I know what it's like. That's in north and east of Ontario. And then Boardman, Oregon, to another site up here. These are 2 of my field sites for another project we had, both of which had composite barriers. Site S again. Site E is another site in Wisconsin. This is a site where they're doing vertical expansion, where the cover was essentially being removed from the facility, and so we had an opportunity to exhume that. And then another site, Site F, in the southwest corner of Michigan. And these are the profiles, again, varying thicknesses, but all of them having a composite barrier, geomembrane over a GCL. And we went in and exhumed these. Interestingly enough, we saw very different types of behavior. This is what we expected we would see when I exhumed that first composite barrier. This is actually the one at Site A. This is Apple Valley, California. This is on the edge of the Mojave. So if there's a site where it's going to be dry and hot, this is it. All right, they get 4 inches of rain a year. At the edge of the Mojave Desert. Look at this GCL. Look at that exhumed GCL. It's wonderful, beautiful material, gel structure. Here's site B. Now it looks a little different. Site B, also in a very dry climate. Eastern Oregon is very arid, not quite as arid as the Mojave, but probably 6 inches of precipitation a year, very arid, but a very different structure. Notice the bentonite here doesn't look nearly as soft and compliant. We can actually see some of the residual or remnant granules, and we can see cracks between those. In fact, if we zoom in a little bit, you can see those cracks very clearly. So this is a different behavior. Two systems, similar climate, similar type of hydrologic environment, geomembrane on top, but two very different behaviors. Why are we getting that? We're beginning to ask these questions. We begin to look at our data, our swell index data. Again, we see all of our sites where we have composite barriers have undergone some transformation. The swell index here for these sites is lower than what we get for a new GCL, which would be up here above about 26 milliliters per 2 grams, depending on the brand that we're using. So there's been a transformation. Some of them, even though they have a geomembrane, are completely transformed to a calcium bentonite, typical of a calcium bentonite. So we see a transformation in the swelling behavior, even with a geomembrane on top. We see the mole fraction of sodium. See essentially no sodium, very little or no sodium in these GCLs, and a reduction in the amount of sodium on these, just depending largely on how long they've been in service. And water contents, these are all underneath the geomembrane. As we might expect, they're fairly uniform. This site B, though, was quite a bit drier for a reason we'll get to in a minute. But they're fairly uniform. They've had a subgrade. GCL's been placed in the subgrade. It's hydrated in the subgrade. It's being a geomembrane on top, so it's not wetting and drying very frequently like we'd see for the conventional GCL sites. And the hydraulic conductivity data were all over the map. All right. Wide ranges of hydraulic conductivity. And the other thing that we found, in contrast to the other GCLs, they were very sensitive to subtle variations in the chemistry of the permeate liquid that we were using. We had, in some cases, we used deionized water. We got very low hydraulic conductivities. Other cases where we're using a very dilute calcium solution, we had higher hydraulic conductivities. And so there was this permeate sensitivity that we observed, and we're going to just talk about that briefly in a moment, and why it's how we might select waters that are realistic. So depending on what water we use, we got different results. It's very important that we learn from this to use a water that represents the field condition as precisely as possible. The other thing is we observed is some very interesting behavior with a few of these samples in the middle. These were samples that we exhumed where they actually had preferential flow through the GCL. These are samples where we actually put some rhodamine dye in the solution. You can see the dyed flow paths in the GCL shown in these photographs. Dye running right along the needle punching fibers, interestingly enough. Here's another one. This is site F in Michigan. This is site E in Wisconsin. Again, here's rhodamine dye running along these needle punching fibers. So there's some other phenomenon that we never thought about is coming into play here. We're not sure about that. I'll talk about that briefly in a minute. So one of the things that we observed from that data set is that the permeate chemistry that we use to test these GCLs was particularly important. Even these subtle variations, just subtle changes in molarity. And we looked at this. We described the water chemistry of permeate solutions for bentonites using two parameters. One, what we call the cationic strength, which is like the ionic strength, but just without the anions. So it's just a cation-driven strength. So essentially a gross measure of concentration. And then we have another parameter called RMD, which is essentially describes the relative abundance of monovalent and divalent cations. So high RMD solutions are solutions that are primarily monovalent. Low RMD solutions are solutions that are primarily divalent cations. And we've actually looked at a great deal of soils from around the country here, about 15 so far, and measured both the cation strength and RMD of the pore water, and we get quite a variation. We find that the cation strengths are fairly low, as we'd expect, and the RMDs tend to be very low as well because they tend to be predominantly divalent. From this, we've been able at least to recommend some solutions. We have what we call our conservative water, which essentially is divalent, as you'll probably see in the field, but not a purely divalent solution. In contrast to, for example, a standard water in ASTM D5084, that's the red dot here. I lost my cursor again. Red dot over here, that's standard water. And we now have in ASTM D5084 the conservative water, and we also have the average water as well. This red cross are waters that are in the standard for and are recommended for testing exhumed samples. So, other things that we observed to those GCLs that didn't have preferential flow, hydraulic conductivity, again, very much driven by the water content of the bentonite. We saw water content was important here, but here we don't have wetting and drying occurring. It's just hydrated bentonite, but again, the water content is a big player here. We need to get the bentonite wet, get it into that gel structure, and then prevent that gel structure from being altered. The specimens that had high hydraulic conductivity had low water contents. Those that had low hydraulic conductivities had higher water contents. And what we found is that those water contents were very closely tied to the subgrade water content. And in fact, all of the specimens that had low hydraulic conductivity this is mislabeled, I apologize over here. These are, yeah, I got a goof up over here. This says hydraulic conductivity, but these numbers aren't right over here. Well, let me just say what this graph is supposed to show. What we found is all of the specimens that had low hydraulic conductivity had higher water contents, and all of those were placed in subgrades that were compacted wet of optimum water content. If the subgrade was compacted dry of optimum water content, there was not sufficient water to adequately hydrate the bentonite, and what was actually happening in the field is that the bentonite was exchanging. We were getting a calcium for magnesium exchange without the presence of water, and we never got a full osmotic swell or a low hydraulic conductivity. So the mechanisms that we saw, we start off with a subgrade, as we see in the bottom, a GCL placed on top with some sodium on it. We're placing it on the ground with a geomembrane on top, and as we place it, water will migrate actually from below to hydrate the GCL, moisture migrating up, hydrating the GCL. And it'll move up, and we'll get a nice swollen structure if we have a wet subgrade. If we have a dry subgrade, we don't have enough water, we'll end up with a very modest amount of swelling. And in fact, we never get into that osmotic swollen state. Over time, we'll get exchange of calcium for the original sodium, and we'll end up with retain a swollen state here. Perhaps it'll compress some, but largely a gel structure. Whereas this dry subgrade condition will end up with never having sufficient water to actually get out of the crystalline state, and we'll end up with a much more permeable GCL. And so we end up with flow paths that are very small for wet subgrades and large on the right for dry subgrades, because we remain in that crystalline swell state. So the chemistry and the physical behavior are tied together. We did some experiments in the lab to prove this out. These are essentially just a subgrade on which we placed a GCL. We wrapped it in a membrane, put in a flexible wall permeameter, and then hydrated it for different times. Again, these are fairly long tests. We did these for a dry subgrade and a moist subgrade, and what we observed is that, again, the water content would accumulate, and over time, if we had a dry subgrade, the water content of the GCL was dry, and our laboratory test mimicked our field behavior very well. We see that in the moist subgrade as well, that the laboratory test would approach, here in this case, about 70%, and that's largely what we observed in the field. We look at the hydraulic conductivity of these materials in the exchange complex. What we see is that over time, as we're hydrating the GCL on these subgrades, that we're gradually having a reduction in the amount of bound sodium. That's what's shown here. And the sodium fraction in the bentonite is being reduced. That's transforming it to a calcium or a magnesium bentonite, reducing its swelling capacity and altering its hydraulic conductivity. And if we look at our hydraulic conductivity, again, a dry subgrade transforms to a calcium and magnesium bentonite, never has the opportunity to go into osmotic swell, and ends up being a very permeable material. For example, a moist subgrade, on the other hand, shown here at the bottom, has a much lower hydraulic conductivity, even if it undergoes some cation exchange. So the only question we have remaining in the last couple of minutes here is this preferential flow phenomenon that we observed. Everything else we've been able to explain based on the physics and the chemistry of the process. The only thing that's kind of hunkering out there is this preferential flow phenomenon. Very unusual behavior. We had these almost these oxide stripes that were in the needle punching that we observed. We were trying to understand what was going on. And what we did was to understand how GCLs hydrate when they're placed on a subgrade. So we did some experiments, which I'll illustrate in a minute. But you can see we pull out some of these needle punching fibers. Look at all the oxides present in these fibers. It looks like almost like tar in there. All right, this is a fiber that's been pulled out from the GCL. So this is a cross-section of a GCL. We put GCL on a moist filter paper. We then allowed that filter paper to wick up water that had rhodamine dye in it and essentially hydrate the GCL from the bottom up. That's what's occurring. All right, so you can see in the bottom here, we see the red rhodamine-laden water at the bottom, the needle-punching fiber. It looks kind of gross, actually. We'll go back and just look at this one more time. But here was the fiber. The water makes its way up through the fiber, shoots up through the fiber, hydrates the bentonite around the periphery, and then this kind of swollen zone moves back out. So we'll just watch that one more time again. Shooting up, moving out, and then propagating. And what we believe is happening in these is that as that water makes its way up through the needle-punching fiber, it hydrates the bentonite around that. There's some osmotic effects there that are preventing the migration of cations from moving into the bentonite. That's resulting in essentially an accumulation or a concentration of cations in the fiber and ends up with precipitation actually of metal oxides within the fiber itself, which then form preferential flow paths. And that's what we found essentially, is that this concentration within the fiber is what seems to be precipitating, in this particular case, manganese oxide that was present in the pore water in the subgrade. So what have we learned here in my last couple of minutes? I think there's some simple lessons. Regardless of our cover system, sodium bentonites used in covers will transform to calcium and magnesium bentonites. We find that to be almost universal. I say that almost because there's a couple of cases where it doesn't occur. Almost every case. In fact, we found that in liners, too. We've just completed a study on composite barriers used in liners that over a period of about 4 years, a sodium bentonite placed on a traditional subgrade overlaid by a geomembrane will transform itself into a calcium or magnesium bentonite. That isn't necessarily negative, it's just a phenomenon that does occur. That occurs in all barrier systems wherever a GCL is placed against another soil layer, almost all cases. If that occurs and the GCL desiccates, we'll get a very large change in hydraulic conductivity. That's because we've taken a material that has high swelling capacity, changed it to one that has low swelling capacity, and when it dries and shrinks and cracks, it can't swell back up and heal the structure. And so this, if we allow it to desiccate, we're going to end up with a very permeable system. Without desiccation, we'll end up with just a modest change in hydraulic conductivity, just about 2 times 10 to the minus 8, about a factor of 10 due to that transformation from sodium to calcium form and the modest reduction in osmotic swell that occurs as a result of that. Lessons learned, 2, if they're overlain by a geomembrane, the hydraulic conductivity varies a lot with the hydration condition of the subgrade. We get very low hydraulic conductivities if our subgrade is moist enough. And what we find is that a specification for that should be that the subgrade should have a water content that's at least optimal. Optimum or a little bit more. There are other unintended consequences of that what we need to think about as well. We do also find that the hydraulic conductivity exhumed GCLs can be very sensitive to just subtle variations in the chemistry of the pore water. So it's very important that we use a pore water that replicates the field reasonably well. And then finally, these preferential flow paths that we observe, that is a phenomenon. We don't fully understand that. That's something that we need to be thinking about and trying to understand that. Some lessons for practice that come out of this for designers, and this is really where we're coming back full circle in the end, that's where we want to get at, is that we want to use GCLs. If we're using GCLs in cover systems, we need to use them with a geomembrane. They're great in composite systems. Used by themselves, they are prone to problems. And so we shouldn't use them in isolation. We should use a composite barrier. A geomembrane GCL is a fantastic barrier. We've seen lots of great field performance from that. That's a system that works very well. And when we do that, we want to ensure that the subgrade has adequate moisture content to allow osmotic hydration of the bentonite. That needs to be at least optimal water content. But when we do that, we also need to think about other things. When we bring up the water content of the subgrade, we also potentially bring in shear strength issues. So there's unintended consequences that we need to be thinking about as well. And then finally, and at least from a testing point of view, that we need to use waters that replicate field conditions at least reasonably well, and we built that into the ASTM D5084 standard, the most recent version of that, that's come out in the last year. And so all of that work is distilled in 3 very simple principles for design. Use GCLs in a composite barrier system, use a subgrade that's adequately hydrated, and then if we are going to test GCLs, make sure that the pore water that we use or the permeant water represents the pore water in the field. 3 very simple recommendations distilled out of the research process. So that's the end. I finished in 60 minutes. I practiced that. I got right on the money. There's been a lot of people who have helped us with this over the years. We're really fortunate to have a collection of funding agencies, primarily, most importantly, the U.S. Department of Energy and our CRESP consortium. We're recently in its 5th generation, and it's completed its 18th year of support on environmental management for the U.S. Department of Energy. A collection of students and postdocs as well that have worked on this. And I also want to thank especially Joe Scalia, who's done a lot of this work. Joe, are you here? Yeah, there he is, Joe. Stand up, Joe. Yeah. Joe's done a lot of this work for me. Thank you, Joe. You've been a great asset. All right, so I'll finish there. Thank you.